Okay, welcome to our Chapter 13 video for Strength of Materials. In this chapter, we're going to look at shear and moment, and we're going to learn how to make shear and moment diagrams that will allow us to determine the amount of shear and moment in a beam at any given point along its length. So let's start by talking about what are shear and moment. So let's say we have a beam. We have a simply supported beam with a pin and roller connection. And let's give it some height. And let's say we apply a load to it. This beam is going to have reactions at either end. And so if we look at just part of the beam here, like a free body diagram, we have the reaction force pushing up on this side and a load being applied right here. If we were to slice this beam right along that point and look a little bit more closely at it, I'm going to draw the beam here and kind of show how we broke it right there. What we have here is we have a case where we have an upward force on this side of that plane and a downward force on that side of the plane. And that is causing shearing to occur. Like in the diagram up here, this is an example of shear. Shear is basically just a force that is created when forces are acting parallel to a given plane. So this is the vertical plane. We have forces going down, forces going up, and it could potentially cause failure in this beam, like is shown here. It just splits right in half into two parts. One half goes up, the other part goes down. We use the letter V to represent shear. Don't ask me why, I don't know. I guess S was probably already taken by something else. So it's V for shear. And this is the sign convention we use when you're reading from left to right and the first force you come to is pointing up and its partner is pointing down and it's causing shear in this direction. We're going to call that positive. And when the opposite is true, when you're going left to right and the first force you come to is down, and the next one just on the other side of this cutting plane is up, and it's causing this type of shear, we're going to call that negative. Okay, the other type of force that occurs within a beam that causes stress is bending. So bending is caused by a moment. When a beam is bending, it's actually a combination of forces. There's tension in the bottom of the beam. So you can kind of see in this beam, if I were to draw like a bunch of parallel lines, or lines at least that would have been parallel before the beam was bent, you can see that the bottoms of these lines are going to get farther apart. That's because the bottom of the beam is in tension. It's being pulled apart. Whereas at the top, it's in compression. We have forces acting down. And as you may recall from our statics class, when you have a pair of forces like that, when you have a pair of forces that are acting parallel to each other in opposite directions, that's a couple, and there's some distance away, so you have a force, two forces actually, times a distance. A force times a distance results in a moment, and this moment causes bending to occur. When a beam bends in this way with tension in the bottom and compression in the top, and it kind of makes almost a smiley face, we're going to call that positive. That's the way I remember it. So, smiley face, positive. When it bends the other way, when compression is in the bottom, tension is in the top, and it bows this way, it bends kind of like in a frowny face, that's negative. That's a negative moment that's causing bending to occur. So we can analyze a beam looking at it as a free body diagram and determine the amount of shear and bending at any point along that beam. Let's start by looking at an example where we are asked to find just one at one point the shear and the moment. This is example, oops, switch over to the pen tool. Come on. There we go. Example 13.4 from the textbook. We have a simply supported beam that has a uniformly distributed load of 2 kips per foot and a single point load of 10 kips. We're asked to find the shear and moment at this point right here, which is 7 feet over from the left support. So first thing we need to do is determine our 2 reaction forces. We need to know all the forces that are present in order to find the shear and moment. So let's start by finding the reaction forces. So if you'll remember from statics, we can sum the moments about any point. I'm going to sum the moments about point A. And so the sum of the moments about A is equal to the 10 kip load. It has a moment arm distance of 4 feet. And it causes a clockwise rotation, which we are going to call negative. That's a negative moment. And the 2 kips per foot is spread out over the beam length of 12 feet. So the total amount of this load is 24 kips. 2 times 12 is 24. And so we can replace the distributed load with one single point load, as is shown here, that is 24 kips placed at the geometric center of the beam, which is 6 feet over. So we have 24 kips times 6 feet. And it also causes a negative moment in the negative direction. The 2 of these moments are going to be resisted by the reaction force at B, and it's going to cause positive rotation in the counterclockwise direction. So we have the reaction at B times a moment arm length of 12 feet. So if we sum, or rather solve this equation, this is all equal to 0, by the way, solve it for the reaction at B, we find that it is 10 times 4 plus 24 times 6, all divided by 12. And that equals 15.33 kips. So our reaction at B is 15.33. In order to find the reaction at A, we just need to sum the forces in the y direction. Sum of the forces in the y direction must equal 0. And so that's equal to 10 kips going down, minus 24 kips going down, plus 15.33, that's the vertical reaction at B, plus the reaction at A. And so if we solve for the reaction at A, the reaction at A is going to be equal to 10 plus 24 minus 15.33. And so that gives us the reaction at A equal to 18.67. So that is up here 18.67. Okay, so we've got our reaction forces. Now we can start to find the, start with the shear, and then we'll find the moment at this point right here. So I'm going to slide over here where I have this diagram copied again. This time I've got the reaction forces labeled on it. And so if I want to find the amount of internal shear in this beam at this point right here, what I basically need to do is kind of cut the beam right at this plane, and then treat whichever half of the beam I choose as a free body diagram. So I'm going to choose to look at the right side of the beam, because on the left side we've got the applied load and the reaction force and the distributed load. Whereas on the right side, we only have the distributed load and the reaction. So there's a little less going on. So just below the beam diagram, I'll draw a free body diagram of the right side of the beam. And so I've got the reaction force going up of 15.33 kips. These are kips we're dealing with. And I've got this distributed load of 2 kips per foot. The span length of just this right half, because this is 7 feet over and the total span is 12, so this distance is 5 feet. So I've got a 5-foot span length, 2 kips per foot, so that's a total of 10 kips. So I can essentially replace the distributed load. Let's see, why don't I change my pen color here to show I'm replacing that distributed load with one single point load that has a magnitude of 10 kips. Okay, and so what I want to do is I want to find out, okay, I've got 10 kips going down, 15.33 kips going up. So the sum of these two is going to be going up. There must be some internal shear acting down right along this plane here so that everything cancels out in equilibrium. So what I want to know is, let's forget that for a second, or let's do this. Let's scribble it out in black. Okay, forget I drew that one. And what we want to know is what is this amount of shear that's going to cancel out all the forces here and leave this free body diagram in a state of static equilibrium. So if I sum the forces in the y direction, it is going to equal, and I'll label this V for shear. I'm going to have the V shear going down plus 10, no, minus 10. Let's switch that. Scribble that out. Switch back to blue. Okay, V going down, minus 10, plus 15.33. And so that is all going to equal 0. And when I solve for V, V is going to be equal to 15.33 minus 10, which is 5.33. So the shear in the beam at this point is 5.33 kips. And on the left side of that plane, it's going down. The sum of these forces here is going up. And so if you remember that sign convention for shear, that's negative shear. Negative V. So I should label this as a negative. That is the internal shear at this point. So right here, I can label in here V equals negative 5.33. So I found the shear. Now let's find the moment.